Hello there. So today we're going to talk about repeated measures designs. These are my favorites, my specialization. With repeated measures designs, we're comparing the same participants on different treatments. For instance, we could do, well, they're also known as within subjects designs, repeated measures designs, panel studies. There's different ways to to discuss repeated measures designs. Okay, so that's just a couple of different synonyms there. What characterizes a repeated measures design is that you have the same participants receiving two or more treatments. For instance, and I just use the term treatment loosely. Like for instance, I could be comparing sodas. Like, does Coke taste better than Pepsi? Or something like SAT test scores before and after tutoring, smoking abstinence, that's say three different time points like pre-patch, post-patch, 12-week follow-up. You could do studies that have thousands of time points. I mean, with the changes in the way we're collecting data now, like with smart watches and other apps, we're getting lots and lots of data. And so there's a lot more we can do with analyzing repeated measures data. But again, it's the same individual receiving the different treatments. And I use the term treatment loosely here, okay? Just for your just to make it to simplify things. There are some benefits to within subjects designs. One, you control for personal differences because you're really unlikely to change a lot over the course of the treatment unless you're young and there's maturation. So with kids, we have to be careful when we do repeated measures designs because maturation does occur, and we'd have to control for maturation in some way. We also end up significantly reducing the number of participants, which is very, very important, right? Whoops, yeah, I had this right first time here. As an example, well, actually, it should be 10. Yeah. As an example, like let's say I'm comparing two groups, say a drug called drug D. We're comparing drug D to a placebo and its effects on something like depression. With the between subjects design, we would have perhaps 10 people per group, right? But I could accomplish the same with a within subject design with 10 individuals because the same individuals receive both the treatment and the control. So, I mean, there's this cost effectiveness to these studies. Like, for instance, if I'm paying everybody $100, we're going to have $2,000 versus $1,000. So we save like half of the amount of money, right? So there's and it certainly, and that's certainly one big benefit of doing a repeated measure design. And we also have the benefit of being able to analyze trends. So we have a linear trend, a quadratic trend, a cubic trend, what have you. And again, when we're getting to these large amounts, something that we'll talk about later is when we get to large amounts of data, sometimes the trend analysis isn't that relevant because there's so many fluctuations over time that trend analysis isn't that important. However, when we're dealing with small amounts of data, like say 5, 4, 3, even 6 or 7 time points, these trend analyses are important. Some drawbacks, we have order effects. So depending on which treatment one receives first may have an effect on later performance. So to deal with that, what we do is we randomly assign people to different orders of the treatment. So for instance, participant one may receive the treatment first, followed by the placebo. Participant two might receive the placebo first, followed by the treatment. So that way we can eliminate any type of order effect. There can also be carryover effects. And I can only think of this, best example I have is when you're comparing tastes on some product. Like say if we're looking at wine, when you're old, if you're old enough, you go on a wine tasting tour. When you do wine tasting tour, you're tasting many different wines, and each wine will have a carryover effect to the next wine. So it'll taint the way you perceive that new wine, right? So the taste of the old one would taint that perception. The way we deal with that in wine tasting, or somebody deals with that in wine tasting to give you some bread or something to cleanse your palate. But that's an example of a carryover effect, and this occurs in repeated measure design study. So you need some sort of a washout period. So whatever the effect is of the prior treatment will disappear. When we're dealing with repeated measures designs and there's only two related treatments, we use what's known as a paired samples t-test. You should be familiar with this. So this is an interesting test. It's very similar to the one sample t-test. One of the reasons for that is that you have the same people, so we don't have to worry about differences in variance differences between different groups of people. So we can treat this the same way we would treat a one sample t-test. Our null hypothesis in such a test would be that the means from, say, time 1 to time 2 are equal, or treatment 1 to treatment 2 are equal. And we could say the means are not equal. It's a two-tail test that's non-directional. We use this paired sample t-test, and the equation looks at the mean difference divided by the standard error of the mean difference, right? So we get this is basically the same thing you have with the one sample t-test. So let's try this here. So I'm going to do this one, and then I urge you all to try the other one. Using the mski.sav dataset, did skiers perform better after a sports psychology treatment? So imagine there was these skiers who were racing down this run, and it's a giant slalom run. We clocked them pre-receiving this mski treatment, and then after to see if there was any change in their performance. So let's go ahead and take a look at this. So go to SAS here. And here it is. So I'm using this data set called mski. You can download that from Canvas. And if you look at the t-test here, of course, as usual, we initialize this procedure PROC t-test. We give it the data location in the library and then the file, and then we say paired, because this is a paired t-test. We have time 1 by time 2, and then hit run. There you go. So let's run this little guy here, and we get our results. Basically, what I'm looking for here is whether or not we have a significant difference. I mean, but you can also look at the difference score and its distribution. So we want to see if it's normal, and it's not quite normal. It's a little bit off there, right? And then there's other statistics we could look at as well, or other things we can look at, like the QQ plot indicates that there's divergence from normality. Sometimes it's not a lot at the tail ends, right? So it's just interesting to look at those. But what we really are truly interested in is our t-test value. And we see here that, well, first of all, we see the mean difference is 1.2653. We had n equals 15 participants. This is our, excuse me, 95% confidence limit. So our null hypothesis is that the mean difference is 0, right? Because either there's no difference or there's a some difference. And since 0 does not, this interval does not cross 0, that's an indication that we probably have statistical significance. And we look at our t-test value with 14 degrees of freedom, and we have a p-value of 0.0181. So this is statistically significant at an alpha of 0.05. That's a paired samples t-test. All right, let's move on. There's a lot to cover here today. And I have one for you to work on. There's a data set called spider.sav. And in this study, you have spider phobics, and they are either shown a picture of a spider or are shown a real spider. And the question is, where do they have greater anxiety? So I would use a paired sample t-test, okay? When we have 3 or more related treatments or repeated measures, we would use what's known as repeated measures ANOVA, okay? If we compare repeated measures ANOVA to the traditional between subjects ANOVA, that's the ANOVA most of you have learned already. We partition that in conventional ANOVA or between subjects ANOVA, we partition the total sum of squares into between and within sum of squares. Within sum of squares is our error sum of squares. So we compare between to within, that's how we get our F statistic. In repeated measures ANOVA, we partition the within sum of squares, I don't need that twice, into model and residual. So model would be the part that's due to our whatever our model is. Our model would be how many different treatments we have, like maybe or time points we have, right? So we're proposing that that'll show why we have change. And then we have our error too. So we're not dealing with this between subjects sum of squares anymore. So we're just looking at the within and we're partitioning that into the sum of squares due to the effect and then the error. And we'll use that to calculate our test statistic. Our hypothesis in a repeated measures ANOVA is that the means are equal, our null hypothesis. And our alternative is that at least two treatments are not equal. That's kind of what we want, but we don't know which ones they are. That's something where you'd have to test. Our test statistic is an F statistic. We have the mean square model divided by the mean square error, and our degrees of freedom are for the degrees of freedom for the treatment and for the error. Our assumptions are that the data are normally distributed and that we have something known as sphericity. Some people might talk about compound symmetry, but we're looking at sphericity. The variance of the differences between the treatments is equal. That's what the assumption is, right? So, all right, we can test for that using something known as Mauchly's test for sphericity. So the null hypothesis basically is that the variances are equal, and the alternative is that they are not equal, right? So if we reject the null hypothesis, we'd say sphericity is violated, right? If we don't reject the null hypothesis, we say sphericity is met. This is using the univariate ANOVA, where we're just looking at the effects of whatever our predictor variable is on our outcome variable. So if sphericity is, we cannot assume sphericity, we can do a correction to our degrees of freedom using this epsilon value, right? So we'd multiply our degrees of freedom by epsilon. However, some researchers say that we should actually consider, we should be okay using, not assuming, well, we're okay assuming sphericity or not having to adjust our model using epsilon if our p-value is somewhere between 0.05 and 0.001. Okay, so that's something that you have to look at. But if you do reject the sphericity assumption, you don't even have to worry about the greenhouse geyser estimate or the other, or adjusting your degrees of freedom for epsilon. What you could do instead is just use the multivariate test because these do not require sphericity. So you'll always get multivariate tests included. So there are some assumptions for this. Actually, we have four choices for multivariate test statistics. All four are the same for a repeated measures design without predictors, but we have predictors. Wilks lambda is the most popular of these four choices. It's the multivariate equivalent of the R square, the proportion of the general variance in the dependent variable. Then we can also, of course, do post hoc comparisons. Something we may want to do is compare each of our repeated measures to the original. So compare each treatment, and then this is called simple comparison. We could do a polynomial contrast, a simple contrast polynomial, or repeated contrast, which compares subsequent measures to the last. So 1 to 2, 2 to 3, etc. All right, so let's do some examples here. So as a dedicated instructor, I want to know whether taking a statistics series would improve students' inherent math abilities as measured by a 100 point point assessments. So I had students complete the assessment before they take the first statistics course, after they take the basic course, and again, after they take the advanced statistics course. Which should I conclude? So we're going to use this data set, inherentmath.sav. So let's go to our data. Of course, I already downloaded this. I downloaded this data file. Oop. Let me go back here. I don't need this one. Yeah, here you go. Let's go to our data file for my multivariate stats course. This is our, of course, our programming file. You can see that we already downloaded. We downloaded that data set. Where is it? Interaction. I think I called it math. Yeah, math. I called it math. All right. So let's go here. But so I'm going to use something known as PROC GLM, General Linear Model. And so this is one way of running a repeated measures ANOVA. There's another one that I'll show you after this. So we have to discuss what our classification variable is here. That's our categorical variable. And in this case, I called it high. Now, what I did here was actually, so what I did was go back to the screen here. Let me see if I did that here. So make sure I did it here. I may not have saved it in this version. See. So a student complete assessment before they take a test. Okay, one thing that I did here was I also took the baseline assessment. So there's baseline, basic, and advanced, right? I took the baseline assessment and did a median split. So I cut it into two different levels, 0 and 1. So there's high and low in terms of inherent math ability. Okay, so let's go back then. So what you see here is this class statement that has high. So my variable is called high for high versus low. So 1 is high, 0 is low. Ability at baseline. And my model is baseline, basic, and advanced. So you have three different levels. So this is just like when we run any kind of a regression analysis or any kind of a linear model, we'll have the outcome variable and then we have the predictor. Here, though, we have three different levels of the outcome variable because there are three time points, right? Or yeah, there's baseline, basic, and advanced. And we really just don't want any information. This no univariate command tells us that we really don't want univariate statistics or for any one of these variables, right? We're just looking at the holistic product. And we give our repeated measure some kind of name. I call it competence because we're looking at competence across time. And we need to print all of our good old results there. It has an extra. This could be print E, right? There you go. And then our competence variable has three time points, right? Or levels, three time points, baseline, basic, and advanced. And we're going to use a simple contrast. We're going to compare every subsequent value to the first value. So basically, we're going to compare basic to baseline and advanced to baseline. Then we also suppress a lot of statistics here that we don't really need, okay? So let's go ahead and run this. All right, so we have two different levels of our between subjects variable. Right, so this is the one that we're comparing overall levels of inherent math based on our competence based on what we have as our initial level of competency. So here's our general linear model procedure, just some basic information, like we have baseline is 1, basic is 2, advanced is 3. We look at the correlations among the different levels. You'll notice that they're pretty high. Of course they will, because their baseline is related to the basic and advanced. So this should all be really high. But what I really want to look at is like things like the test for sphericity. When we look at the test for sphericity, we look at this orthogonal component. So this is actually dealing more with something like called principal components. We look at how many of these components underlie our multivariate space, and we're interested in this orthogonal one. This is the sphericity test, so we would reject the null hypothesis, but this p-value is 0.0362. It's not that bad. So we can either continue to use the univariate analyses, or we can go jump to the multivariate. The multivariate is more informative in that we don't have to worry about sphericity. And as I mentioned, we can use Wilks lambda as our test statistics. We're going to look at the MANOVA test criteria and exact F statistics for the hypothesis of no competence effect. So this is basically looking at the within subjects effect that goes from baseline to basic to advanced. And we can see that there is an effect of time, right? So there is an effect of competence. And then we have the next part, which is interesting. This is the between by within interaction, because really that's what we're interested in. Is there an interaction such that those who were high during baseline will differ from those who are low during baseline, right? So that's what we're looking. Yeah, they'll differ in their overall competence over time. And from what we can tell here is that with using the Wilks lambda again, the p-value is really hard. So it's not statistically significant. So we could say that there's a significant main effect for competence or time, basically, but there is no time by I guess baseline competence interaction. Mhm. So this is pretty interesting. All right, cool. So let's go ahead and try and actually here, actually, let me just go back for a second. We do this comparison second to first and third to first, right? And we see that there's a difference in competence between second and first, but the interaction is not significant, which we already know. And then from third to first, there's also a difference, which we'd expect, but there's no a non-significant interaction term. Okay, cool. And then we can write this up. There was a significant change in student inherent math abilities across time. Put in the Wilks lambda of 0.113 and our F statistic, which we get from that table, right? 109.404, and our p-value assessment of change from baseline to subsequent measures suggests that inherent math abilities increased following, excuse me, the basic and advanced courses. So they show those values that we got from the table of simple contrast. Okay, let's do the same now let's see. Oh, let's do the same using the PROC mixed instead, right? So PROC mixed. So this is a completely different way of doing the same analysis. However, to start, we have to change our data from what we call wide format to a long format. Wide format data are data that have each column representing a different variable and each row representing a participant. That's the way we generally deal with data in my courses. However, we can also have data created such that rows can represent different variables, right? So that, like, for instance, if a participant, say participant one, has a measure for baseline, a measure for basic, and a measure for advanced, that individual's data will look like, well, you'll have, their participant ID, let's say it's one, so you'd have one, and then you'd have data for baseline, then you'd have one, and you'd have data for for basic, and then you have 1, and then you have data for advanced. Then we go the same with 2, you'd have data for baseline, 2 data for basic, and 2 for advanced. So what we do is we create a different structure to our data, and we need to do that if we're going to use PROC mixed. And PROC mixed has some advantages. So first thing we're going to do is we're going to convert the data to the long format. So I use the data statement, data mv stats dot long math. So this is again my library, and this is my new file. This file doesn't exist yet, so this is the file we're creating. And we're going to create it based on the MV stats math data set, the one we just used, right? Then we're going to create something called, we're going to create a dependent variable, and our dependent variable will have baseline, basic, and advanced, right? And we're going to call this trial. So trial for baseline will be trial 1, basic trial will be 2, and advanced trial will be 3. Once we're done with this, we're going to drop the original variables, baseline, basic, and advanced, so that we get rid of them. So our data set isn't cluttered. So let's go ahead and run that. We can actually see our output data. So we have our observation, we have high DV, right? And our trial. No errors here, nothing, right? But you'll see you have observation 11. Well, actually, let's start here. Observation 16, 29, and you see there's 3 rows for each, right? So we have our DV. So our DV would be baseline, basic, and advanced. I think it was advanced, right? And that would be trial 1, 2, 3. And then we have trial 1, 2, 3 for participant 29, and so on. And all these individuals are in the high category. Well, they're actually not high in the high category, in the low category, because their high level is 0. Then you'll have those who are in the high category itself. Okay. So you see that it all worked out well. Let's go back here. Now we can run the PROC mix. So in order to run the PROC mix and GEE, which we'll be doing on Thursday, to run those, we have to have our data set up in this format. Let's use PROC mix data equals nvstats.longmath. So that's the new data set we just created. Our class variables, or our categorical or discrete variables, will be observation, high, and then our trial. So we have 3 different class variables or discrete variables. Our model will be the dependent variable. So now we're just using DV because it encompasses those 3 different time points. Equals is predicted by the binary variable called high. Remember, high is 1, low 0. The trial itself, 1, 2, 3, and then so this is the repeated measures variable, right? So this is indicating the within subjects effect. And then we do a within by between interaction. Interaction terms are products, right? And our repeated measures variable is trial. Okay, we have compound symmetry. So this is just telling us how our variance and variance covariance matrix is structured. All right, let's go ahead and run this. Check this out. This is cool. Here's our 30 observations, the way they're set up, 1 through 30. And we got another variable called high, where it's 0, 1, and trial will be 1, 2, 3. So everything makes sense, right? All right. So let's look for anything interesting here. So now we don't have sums of squares anymore. That's something that's different. Instead, what we're dealing with is these log likelihood values. This is something we should get used to because we can make model comparisons using all these new tests like the AIC, the BIC. All of these are ways of testing. It's a smaller is better, but really they're only useful when we're comparing models. So this is one model. We'd have to compare it to the other smaller is better, right? So if we had compare two models and one model has a smaller BIC, we say, oh, this model is superior to the other model. So this is something totally new that we have to deal with. And we also have this likelihood ratio test, which follows a chi-square distribution. And what do we have in terms of our effects? Well, there's an effect for this variable high versus low. So there's a significant effect for that variable for trial. So there's a between subjects effect, there's a within subjects effect. However, there is no between by within effect. So that's why we see high by trial. It's not significant. It's a p-value is 0.1598. So while there's an effect for, it's like with treatment, you have an increase in whatever our variable was here. Uh, Competence. We have an increase in competence over time. And there's the difference between those who are in the high and low group. That we know. However, there's no interaction between the two. So there's no high by trial interaction. So we won't see a different effect of time based on whether one was high or low at baseline. All right, cool. Conduct a repeated measures ANOVA to assess the change in depression across time using the DEPRESS-3 data set. So there's a data set called DEPRESS-3. So you want to use that, and you want to do the same kind of an assessment. So let's just open that data set so you can see what it's like. Let's see. Here it is, DEPRESS-3. I just called it DEPRESS SAS. So here it is. I downloaded it. I ran the PROC GLM, right? And to see if there was so there were six time points here, right? So it's a little bit different. There's 6 time points. And we can see that there was a significant effect for time. But in terms of depression by group, there was not a significant effect there. So these are all p-values are very, very high. Okay. So we had 6 different measures of depression across time. And let's see if there's anything interesting here. Repeated measures analysis tests hypothesis for between subjects effects. So this is actually statistically significant for the between subjects effect. Is this using let's look at the multivariate data instead. Let's see if we pass the Mauchly's test for sphericity. Let's check that. Okay, so we cannot assume sphericity. So we're going to use the multivariate test, and here we have a statistically significant result for change over time, but not for change by whatever our grouping variable is. Okay, cool. And when we compare each level to the first level, like 2 versus 1, 3 versus 1, 4 versus 1, 5 versus 1, and 6 versus 1, not all are statistically significant. Let's see which ones are. All right. So this one is not. So 2 versus 1 is not statistically significant in terms of depression. 3 versus 1 is. 4 versus 1 is. 5 versus 1 is. 6 versus 1 is not. And in all cases, the interaction is not significant. All right, cool. Conduct repeated measures, and we did that. Use simple comparisons to compare. Okay, so let's actually go to, all right, let's go to the next part here and do the the PROC mix. So let's start here by running these data. So for every depression variable, I had to link it to this dependent variable that's called dv. Let's go ahead and run that. All right, so it worked because we should have 6 values, 1, 2, 3, 4, 5, 6, and then 6 for the next, and so on and so on. What group they're in. Here's our dependent variable. We'd have 1, 2, 3, 4, 5, 6 different values, right? And our trial, 1, 2, 3, 4, 5, 6, and it keeps on repeating. Okay, so those are our data. Let's go ahead and run this PROC mixed. So again, we have data as MV stats long depressed. Our class, our subject, group, and trial. Subject is our participant variable. Model, we have dependent variables equal to group, trial, and then group to trial interaction. All right, let's take a look at this. Yep, class here it says option statement is not valid or it is used in the improper order. Let's see if what was wrong here. Trial. Let's see what went wrong here. PROC mix. Here it is. I don't know what I must have pressed something wrong by accident. So here are our subject. Subject has, so this is our participant variable called subject, has 61 different levels with 2 groups and then 6 trials. I like how concise the data are. So yes, there's a group effect. So there's an effective group. So this is just looking at the overall mean across all 6 time points. They differ by group. There's a trial effect. So this is across the 6 different trials. There's some kind of a change over time. And in terms of a group by trial interaction, it is not significant. Right there, p-value is way too large. All right, cool. So that's running repeated measures ANOVA with PROC GLM or PROC mix. So enjoy playing around with these data. See, there's more to do. All right, have a great evening.